Hi, this is a video on the section 9.7, which is about type 2 error probabilities and power. If you recall, back in section 9.1, we talked about the types of errors that can happen in hypothesis testing, and we talked about that there's two types of errors. The first one, and by the way, these are errors that would happen without you doing anything wrong. They're just hypothetical. And in order to understand them, we do this thought exercise where we consider that the null hypothesis is either true or false. And so if with a type 1 error, we are in the thought experiment situation where we say, okay, in this case, we're going to assume that the null hypothesis was true, and alpha is the probability of rejecting it when it was actually true. So that's called the type 1 error, and we have been setting out all along that alpha is the probability that this would happen. So it's our risk of rejecting a true null hypothesis. And that other type of error that can happen is you don't reject the null, but it was actually false. And we give this type, the probability of this type of error, which we call a type 2 error, we give that the Greek letter lowercase beta. So we have a probability of beta of a type 2. The flip side of that is that we are that we end up making the right decision. So in our thought experiment, again, if the null is true and we do not reject it, then the probability of this is going to be 1 minus alpha, and we call that the confidence level. And if in our thought experiment, if we can think what would happen if the null is false, we would want to reject it, and that would be the correct thing to do. And the probability of that is 1 minus beta, and we call that the power. And we're going to talk more about this in a minute, because that's the topic of today. All right. The concepts that I'm going to present for power are going to be done using the one mean t-test, but everything applies exactly the same for any hypothesis test. So I want to have a working example that we'll be using today, and that's involving this new model car, which is called an Orion. And the people who make it are claiming that it gets 26 miles per gallon, but there's a consumer advocacy group that doesn't really believe it, and they think actually it might get less than 26 miles per gallon. So that group, in order to make that assertion, has to back it up with more than just a sample mean. So they're going to perform a hypothesis test. So the setup of their hypothesis test is that the null hypothesis is that the Orion car model gets 26 miles per gallon or more. And the alternative is what they're actually wanting to test, and that's why we put that in the alternative. So the alternative is where we put the question that is of interest. So at a 5% significance level, they're going to do this, and they're going to sample 30 cars. So what we want to do is use this example to find the probability of making a type 2 error. And whenever you are going to talk about making type 2 errors, you kind of need to do a thought experiment again, where we pretend that we know what the true gas mileage is. So we're going to do it under two conditions, where the true gas mileage of all Orions is 25.8 miles per gallon, and when it's a lot less, 25 miles per gallon. We're going to assume that the gas mileages of the Orions are normally distributed and that we do know the standard deviation. And again, this is just to make the math a little bit easier so you can focus on the new part I'm trying to teach you, which is the power. So this is going to be our sigma here. So sigma is known in this case. So with a left-tailed test, which is what we are going to see that we have when we look at the alternative, right? It's pointing left. So it's a left-tailed test. We see that the mu naught is 26. The mu naught is always in this position. It is the number in the top right when you set up your hypotheses. And it's 26 miles per gallon. Our alpha was given as 5%, so 0.05. We already know we have a sample of 30 cars, and we know that our standard deviation, population standard deviation is 1.4 miles per gallon. So the first thing we're going to do is we're going to use the alpha to get a critical value. So because it's a left-tailed test, we're going to get the z sub alpha, the negative version of that. So we want the 5% to the left, and so it's really easy. We just do norm S inverse of 5%, and we're going to get negative 1.645. And then the new step that we're going to do is we're going to convert the critical value, this 1.645, we're going to convert it back to what its x value was. And we're going to do that based on the null hypothesis. And we're going to use the test statistic to do this. So since we're doing a z-test, because sigma is known, our test statistic is z is equal to the sample mean minus the mu naught, that's coming from the null, the expected value, divided by the standard error. And the standard error is very specific to the type of test. This is a z-test, so it's the sigma divided by the square root of the sample size. So what we're going to do here is we are going to put in everything we know, and we're going to back solve for the critical x value, which we find is 25.6 miles per gallon. So now that we have that, we're going to go ahead and graph that. On the x-axis, we'll put the null hypothesis. So this is our mu naught. And we're assuming that we have a normal distribution. This is where we start out with we start out believing the null hypothesis, and then we find out if the data suggests we reject it. So we're going to accept a risk of 5%. That's our alpha. And then we find that the value on the x-axis, the x bar, the sample means, is 25.6. So if we see anything less than or equal to 25.6, we're going to reject the null. If we see anything greater than that, we're going to not reject the null. So the first thing we're going to do is we're going to determine the probability of a type 2 error. If the real true mean, so this is a thought experiment because we don't actually know it. We're just going to say if it's actually 25.6. So recall, we already know this. We know the standard deviation of the population. We know the sample size. And we know that by the central limit theorem, so this is chapter 7 material, we know that the sample mean is normally distributed with the population mean as the sample mean of the normal distribution, right? And the standard deviation of the sample mean, which we call the standard error, is sigma divided by the square root of n. So we're going to go ahead and use the truth here. And we're going to say, okay, because that's actually the truth, that's what the sample means will actually be distributed a lot around 25.8 instead of 26. And the sample means will have a standard deviation of the 1.4 divided by the square root of 30. So these are our parameters for mu and sigma for what the normal distribution will be for the sample mean in this case. So the probability of a type 2 error, which means we're not going to reject, we're going to make a mistake, and we're not going to reject that the sample mean is 26 when we know that the truth is that it's 25.8. Okay, In other words, that the null hypothesis is false, because remember, this is the null. So the probability of a type 2 error is finding out what's the probability that we don't reject the null. So in order to do this, what we're going to do is we're going to graph a new normal distribution. It's now not centered at 26. It's centered at the truth. In our thought experiment, we're going to center it at the truth of 25.8. Okay? And now what happens is we're going to plot on here the critical value. Sorry, I got squished. We're going to plot the critical value of 25.6 that we had figured out from before from our null hypothesis. And what we're going to find is that the probability of a type 2 error, which remember we're going to call beta, is going to be the probability that we get a sample mean greater than that critical value. All right, because remember, that's just coming from the way we set up the null hypothesis. So because we want the area to the right, the way we have to do that in Excel is we have to say it's 1 minus the area to the left. So the area to the left is 1 minus the normal distribution at this point, 25.6. But now we use what's the truth in here. We're going to use the 25.8 and the 0.26 for our mu and sigma for this normal distribution around the true mean. And if that's the case, what we get is 1 minus 0.2206 or 0.7794 is this shaded blue area. So that means we have around a 78% probability that if the sample mean is greater than 25.6, we won't reject a sample mean of 26, even when it was really 25.8. So let's just summarize so far. So when we start out with a hypothesis, we use our null hypothesis and we assume it's true. So we draw a normal distribution around that null, and we determine using our alpha, which was given of 5%, what is the value where if we have values of the sample mean that are less than 25.6, we would reject the null versus not. And then what happens is we draw a new normal distribution. So we take this one and we're basically shifting it over and we're centering it over what we believe is the true mean. And we're only doing this as a thought experiment to kind of determine what is this shaded area over here. And we find that it's 78%. And that's the probability of a type 2 error, because remember, if we have any value in the x-axis for a sample in here, we're not going to reject that it's 26 miles per gallon, but the truth was it was 25.8. Now you may say, okay, that's a pretty high probability, but if you think about it, it's not surprising because 25.8 is really close to 26. So it would be really hard to tell it apart. So the power of a hypothesis is the probability of not making a type 2 error. That is the probability of rejecting a false null hypothesis. Right? So that means we did the right thing. We rejected the null and it was actually false. So the power is 1 minus, and this should have had a p here. So it's 1 minus the probability of a type 2 error, and that's 1 minus beta. So going back to where we've been so far, if we looked at the other side, so if this is beta, 1 minus beta is what's to the left. And that was 100 minus 78, or around 22% probability of rejecting the null. Remember, we assume that in the null we're claiming that null claims that the sample mean is 26, and actually it was 25.8. So with a sample size of 30, n equals 30, there's a 22% probability of leading to the correct decision if the true mean is 25.8. And the correct decision would be to reject that it's 26 miles per gallon. And we call that the power of the test. So this is very low power to tell that apart because that's only 22% probability you could do that. So let's go back now and compare how how things look differently when we do our thought experiment. That the truth now is that the true miles per gallon for this new type of car is 25 miles per gallon. So we're going to repeat all the steps, but now we're going to use the mu 25. So the first part we're going to do is not effective because we're just still going to get our alpha, which was a 0.05. It's still a left-tailed test. We're going to still use our test statistic and solve for x, and we're still going to get the 25.6. Where things are going to be different is when we now think about the truth. So assuming now that the truth is 25.0, and we know the sample mean is going to be normally distributed around that true mean of 25 and with a standard error of 0.26. So when we do not reject H0 is when we have values of that sample mean that are going to be up here. And that beta, which is the probability under the curve here, is the probability, right, what I just said, that a sample mean is going to be greater than 25.6. So it starts out exactly the same as we set it up before. And to determine that in Excel, we have to do 1 minus the normal distribution of everything to the left. But now what the difference is that we've replaced we've now used a different normal distribution. We're shifted it all the way over and put it over 25 instead of over 25.8 or where it was for part A. All right, so when we do this, we see we have a lot more area now to the left, and all that's left to the right for our eta, for our type 2 error, is 1%, right? Is around 1%. That if the sample mean is greater than 25.6, we won't reject the null when it was really 25 miles per gallon. So that's going to give us that probability of a type 2 error. But what's on the left, on the other side of this 0.01, right, is 1 minus beta, and we call that the power. And in this case, the power is approximately 99%. That was just actually already calculated as part of the steps we did to get the beta. So it's 99%. If the true mean is 25 and you have a sample of 30 cars, that we will reject the null hypothesis. With any sample, there's a 99% probability that a sample mean will lead us to conclude. We will conclude that we will decide that we will reject the null hypothesis. So we have a lot of power if the true mean is 25.0 to reject a false null. So again, in this situation, this is the same normal distribution that we started out based on a null hypothesis. It's centered at 26. And then what we're saying is actually the true situation in this thought experiment is that the mean was way lower. It was at 25. So when we pull that normal distribution over, we're moving it to the left, but we're leaving this rejection, this critical value here, in the same place. We now have a much smaller probability of doing a type 2 error and a much greater amount of power. So let's consider several possibilities for the true mean. So far I went through 2 of them. So the 2 that I did was, the first one was a 25.8, which is here, and that's where we found that the probability of a type 2 error is around 78%. And then here at the bottom is the probability uh, of a type 2 error if the truth is that the mean is 25. So basically, you just center it on what the truth is, and you can see that the further away the truth is from the null hypothesis, the smaller the probability of a type 2 error or of not rejecting a false a null hypothesis. Notice that when we let the truth be actually our critical value, then we have 50%. We actually like moved the null, so now it's at our critical value. And since it's at the critical value, we don't really need to do any calculations on this one because we know 50% of the data lies on either side of the mean. Okay, that's just a little observation, but you're not going to need to know that. But what I want you to consider is that as the true mean goes further away, you get smaller type 2 error, but you also are getting a larger and larger power as represented by the area in orange that's being shaded. So for calculating a power curve, I want to go through and kind of use this example. So step 0 is we're going to use the alpha that's given. We're going to calculate the critical value. So this is everything we've done already and back solve using the test statistic to get the critical value in terms of x. So we did this already. It was at 25.6. If you recall, our hypothesis was a left-tailed because the alternative hypothesis has the inequality pointing to the left. So the first thing we're going to do to create a power curve is we're not just going to come up with 2 or 4 possible true means. We're going to come up with a whole bunch of them. And you can decide how many you want to do. We're going to do it in Excel, so it doesn't really matter. In this case, we're going to just choose somewhere between 24.8 to 25.9. We're going to do increments of 1/10. So 24.8, 24.9, 25.0, all the way up. And it's just basically depends on the specific situation, how much granularity you want there, and where your concern is. So where this consumer advocacy group concern is, they would be deciding what power they need. And I'll show you in a second how that, once we set this up, how it can lead to decisions. So the first thing we do is we're going to construct all this steps, and it's a good practice that they be equal distance from each other. So let's go ahead and get that started in Excel. All right, so step 0 is this stuff up here. So we have a sample size of 30, and we have an alpha of 0.05, and we have critical value. So that's going to be equal. Because this is a left-tail test, I know that I can get the norm. Norm S inverse for the left tail 5% of the values there. So I get that negative 1.645. I know that the mu naught is coming from the null hypothesis, and that was 26 miles per gallon. I was told the population standard deviation, or the sigma, was 1.4. And I can calculate the standard error that goes in the denominator here. So I'm going to say that's going to equal the sigma divided by the square root, SQRT, of the sample size. And now I have that standard error. And now I'm going to calculate the X bar critical by doing the algebra to solve for X. So I'm trying to solve for the X in this equation. I've got to multiply both sides by the denominator, which is the standard error. So I'll start out by saying equals the critical, the Z critical value, the z, negative z sub alpha, I'm going to multiply that by the denominator of both sides, which is the standard error. And then that'll leave me x bar minus 26. So I'll have to add 26 to both sides. I'm going to add the new naught to both sides. And if you aren't sure, you can do this algebra out on a scratch piece of paper if you're not comfortable doing it in your head. But this is where we get the 25.6 value. So this we already have done. Now that we've done that, what we want to do is we want to go ahead and set up the step 1 here, which is setting up the true mean mu. So let's go here, and I'm going to call this step 1. And we'll call this true mean. And in an Excel, if you want to put in a Greek letter, you have to go to Insert and go to Symbol, and click on the mu. Okay, so now my true mean mu is going to be started at, I think we said 24.8. So let's go ahead and put 24.8 here. And then we're going to have increments of 1/10. So I'm going to say equals 24.8 plus 1/10. And that'll give me the 24.9. Now, because this is a relative reference, it points to the cell above it and adds 0.1. I can continue this same pattern by copying this formula down until I get to the 25.9. Right, so now that I have all my true, my increments, I'm actually going to go one more and go up to 26.0 because that'll take me all the way to the null hypothesis, right? So this is the null hypothesis, is that the true mean was 26 or more, but this is the lower bound of what it would be. Okay. Okay, so the second step is we're going to construct a work table of this form in Excel. So let's get our Excel here. We're going to add the probability of a type 2 error. And to get a carriage return on a Windows, I'm not 100% sure how you do it on a Mac, but on a Windows, you hit Alt and Enter at the same time. And that allows you to get a carriage return within a cell. Insert close, and then I have this here. And then the last one is we want the power. So the power, again, Alt Enter, and I'm going to go, this is 1 minus the beta. Okay. So now I have this table, and I'm going to set it up. So let me go to the home screen, and in the font tab, I'm going to put a big border around the outside of that. I'm going to add a line under the top, and I'm going to center everything. So I'm selecting it. I'm going to go to alignment, and then I'm going to center. I'm going to make my headers bold. So again, font bold. I'm going to make this a little bit bigger. It's a little easier to read. Okay. All right. So now I've set that up. So the next thing is we're going to go ahead and for each value of mu A, and mu A means actual. So let me just go back a second. What we're going to assume in our thought experiment, basically, as we develop this power curve, is what if the true mean was 24.8? Then, okay, what's the power for that? What if it was 24.9? What if it's 25? So each one of these we're going to refer to as mu sub A for actual, or true mean. So we're going to use each one of those, and we're going to calculate the type 2 probability. So let's go ahead and do that. So to do that, we're going to remember that beta is the probability of a type 2 error. And basically what you're going to do is just change the actual value of the mean in the normal distribution. If you're doing a normal distribution, or the mean, if it's a t distribution, you would just change the mu again in that. And remember that beta is the probability of a type 2 error. Because we're specifically doing a left tail test, our betas are going to be to the right. So the probability of not rejecting the null. Okay, so it's 1 minus the probability. And remember that the value at the is this x critical, and this is coming from the null and the alpha. Okay, so we get that value, and we're going to plug into the normal distribution. We're going to plug in that critical value, and what we're going to change every time is we're going to be switching these out. This is going to stay the same, this will stay the same, or we always use true to give us our cumulative distribution when we use the norm function. And let's do this in Excel. So let's just move this over a little bit so we can remind ourselves what we said we were going to do. So our probability of a type 2 error is going to equal 1 minus the norm distribution, and we still want to use that same critical value, 25.6, but the mean we're going to assume is this true mean. And I just realized I'm hiding it behind my formula here because I set things to be center aligned. So let me just show you how to avoid that. We'll do the center alignment later. I'm going to select these and go to the alignment and go left alignment, so that when I'm typing in the cell, it's not overriding what's to the left. Okay, so let's try that again. Equals 1 minus the norm distribution of the 25.6, and based on a true mean, so normally distributed around this number, with the standard deviation, which we're going to, because we're dealing with sample means, is the standard error. And we're going to say true. All right, so this is our type probability of a type 2 error of our beta. If the actual sample mean was 24.8, the probability of rejecting the null that claims that the mean is 26 or greater is less than 1%. It's actually 0.11%. So I want to copy this formula down. One of the things I'd like for it to be is not have so many decimals. So I'm going to, sorry, let me undo. So Control Z. Oops. I meant to hit this. This is a way to get fewer decimals. Usually we'll go with 4 decimals when we do these beta calculations. And the other thing is, I think it would be nice to have it centered. So now that I have that, I would like to copy it down. So what I want is this formula to, when I copy it, I want it to point to 24.9 now as the mean, but I still want it to keep pointing to the same values here. So that's a combination of a relative reference and an absolute reference. So in order for the cells at B9 and B8 to not change when I copy the formula, I have to put dollar signs in front of them. So I'm going to put a dollar sign in front of the B and a dollar sign in front of the 9. And then I'm going to put a dollar sign in front of this B and a dollar sign in front of the 8. And what that means is when I copy this formula, Excel won't change the B8 and the B9. But notice if I copy this formula down 1, now it's pointing to a true mean of 24.9. It still kept these pointing to where I had originally said because I froze them. The dollar signs kind of freeze the cell references. But Excel has the power of enabling you to do relative references. So now I don't have to type that formula on every line. I can actually copy it down by dragging it down here. Or some of you know that there's another little trick. If you double click the little green box in the lower right corner, it'll automatically fill it in for you. So now what I know is that my probability of a type 2 error beta, which means is the probability of not rejecting the null, is going to depend on what the true mean is. And you notice if the true mean really is what was in the null hypothesis, then we have 95% probability we're not going to reject it, which is our confidence level. Okay. So the next thing is we're going to use those steps and that relation to get the power. And so we'll fill in all the columns in the table to get that. So this one's pretty easy. This is just going to equal 1 minus the beta is the power. And again, I'm just going to copy this down. Notice that I lost my formatting here. I'm going to go ahead and select these two cells, go up to the font, check this window pane one, and come down to the thick bottom border. So I kind of recreated that a little bit so it looks better. And I'm going to go ahead and center this with the alignment in the center. Now that I did that, I can go back over here and I see that what I need to do is plot the values of the first and third columns from step 2 as points on a graph. And we're going to put a hollow point for the null hypothesis, mu naught, the null hypothesis mean of 26 in our case, and a significance level alpha for us is 0.05. And then we're going to connect the dots. So let me show you how we're going to do that. I'm going to make this a little bigger now so we can see more what we're doing. Okay, so I'm going to select the true mean. So I recommend working in Excel using a mouse. So I just clicked on my mouse and dragged. Now while holding down the control key, I think if it's a Mac, you'll use the command key. I'm going to hold down and drag and get this second column. And then I'm going to go to insert and I'm going to go to the scatter plot drop down and I'm going to select the middle one that on the top line, which connects the dots. So now I have a curve that is showing me the power as my sample size. So let's go ahead and give the axis a title. The primary horizontal, and this is going to be so we're going to call this the true mean. And I'll go to insert, symbol, Greek symbols, true mean mu, insert, and then close. And this is the average miles per gallon for Orion cars. Okay. Notice that I can a lot of times once we have the power, we might want this. We don't maybe need 4 decimals here, so we could actually go to the home tab. We could turn this into percentage, and that's fine. We could add a decimal there if we wanted. Don't really need to. And then you notice that the power, which is 1 minus beta, and these are all probabilities, the y-axis is going up to 120, and that's unrealistic. So it's good form to not have a number on your axes that is impossible. So you can notice I clicked on the axis until I got little blue circles around the numbers on the y-axis. Now I'm going to right-click and format axis. So over here in format axis, I'm going to go to the maximum and I'm just going to put a 1.0. So that just raised that so that looks more normal. Okay, so that's our power curve for a sample size of 30 and an alpha of 5%, when the null hypothesis is that the mean is greater than or equal to 26. So how do you read this? Well, you'd say if the true mean is like 25.4, you have like around 75% power. 76 actually, if you hover over it, power to reject the null, um, being that the mu is greater than or equal to 26. Up here you have, and so here you're at like 25.3. It looks like you have 86% power to reject the null. So this is showing you how likely you are to reject the null if this is the truth. So you kind of want to know going into an analysis how how likely are you to be able to detect the problem if the null is if sorry, how likely are you to be able to reject the null, assuming that you don't believe it. Okay, so let's go back to the slides now. So let's look at calculating a power curve for a different sample size. So I'm going to rename this here and equals 30. And then I'm going to copy it. So I'm right clicking, going to move or copy, selecting create a copy and move it to the end. And then I'll hit OK. And then I'm going to right click and rename this one and equals 100. So now I have another power curve worksheet set up. Everything in here is what I want it to be, except that sample size is wrong. I want to know what happens if we do 100 cars in this sample. Now notice that the curve shifted up. All the numbers shifted up. We have 100% probability if we do 100 cars. Anything looks like at 25.4 or less, we will definitely reject the null and recognize that the true mean is less than 26, as long as this is where the truth is. Okay. Oh, I forgot to show you something. Back here in this, we were supposed to put a hollow point at the null hypothesis value. So I'm going to go in here. I'm going to select. Notice the markers look like they're selected. I'm going to select again. So I only select the one that's at the 26. Then I'm going to right click and go to format that data point. And in the format that data point, I'm going to go to the paintbrush. And then I'm going to choose up here where it says marker. And then click the drop down for marker options. And then I'm going to go to the built-in and I'm going to make this bigger. And then on the fill drop down, I'm going to go to no fill. And then on the border, I'm going to select a different color that it's easy to see, like red. And then that's it. I have it. If I had done that originally, it would have automatically translated over here. Unfortunately, I didn't do it. I forgot to do it. So now I got to do it by hand. So let me go in here and do that real quick by hand. So the marker options, I just want to make it a little bit bigger. I want no fill. I want to make it red. And that's it. Okay. So now we can see that this is, as the truth gets closer to 26, the power to reject that truth goes down substantially. All right. So now what I want to show you is a lot of times when you're making decisions, you want to kind of compare one curve to the other, and it's a little difficult to even have them side by side. So I want to show you how to overlay them. So let's say I want this curve right here. I'm going to select it. Notice it has the white circles all around the frame of it. And then I'm going to copy it. So on a Windows, it's Control C. I'm going to come over and create a new worksheet. And I'm going to go ahead and put it here. And I'm going to rename this worksheet Power Curves. Okay, so now that I have that, I'm going to select it, and I'm going to go to this chart design, then select data. So in here, I'm going to select edit, and then I'm going to go ahead and give this series, what's going to make it different from the other one. So I'm going to say this is equal, this is the n equals 30 scenario, and then I'll hit OK. And then I'm going to add, and here I'm going to select, I'm going to call this the n equals 100 curve. So I'm going to, for the x values, I'm going to come over to the tab that says n equals 100, move this out of the way, and select these values here. And then for the series y values, I'm going to delete what's there. And then I'm going to select these values here. And then hit OK. And now you'll see that we have the two curves overlaid. In here, we need to add a few things. So let's add a chart title. And for the chart title, I'm going to select, there's a couple things that you need to communicate in this power curves so that it's clear. The first thing is that you're going to state what the null hypothesis. So it's the power to reject that the mu is greater than or equal to 26 miles per gallon, and you need to state the significance level, alpha, because those two things if those things change, these curves would change. Okay. And then the next thing that's very helpful is to put a legend. Now, if you're doing this in a Mac, you're going to go up here to add chart element and go to legend this way, and you can select it. I'm going to select it on the top. You can do that on a Windows as well, but on a Windows, you also have these like shortcut buttons. And so the reason it's helpful to have the sample size at the top is because that's a decision driver. Because sample size as it goes up is expensive. It costs both time and money. But if you're really trying to detect if your true mean, if you believe your true mean is less than 26 and you're trying to detect it and you don't want bad luck in a bad sample, you'd kind of want more power to be able to detect it, or increased probability that you will actually reject the null when the null is false. So you can see if the truth is that it's 25.6, with a sample size of 30, you have less than 50% power to detect that it's not 20, that it's less than 26, versus 90% power if you went up to 100, a sample size of 100. So these are used all the time in the planning stages of a study to figure out how much sample size is needed to accomplish what is thought to be the case in the data, in reality, the thing you're measuring. For a fixed significance level, increasing the sample size increases the power, as we just saw. All right, and then the one last slide I want to show you is which procedure should be used. And this flow chart is not extremely useful, really. Well, maybe you'll think it's more useful than I think it's useful, because usually we're going to be up in this top area. So do you have a normal population? And you really only need to ask that question if you have a sample size less than 30. Okay, so it really should have had that as a previous statement, and then had to come down. But so if it's a normal population and your sample size is less than 30, or you could just say or n is greater than or equal to 30. Then it's a standard deviation now. Remember, this is sigma. Is sigma known? Yes, use the one mean z test. If not, we're going to use the one mean t test. All right. If it's not a normal population, but it's symmetric, that's where you can use this method we did not cover called the Wilcoxon sine wave test. It's not hard to do. Just would take You just have to follow the steps on how to do it if you wanted to do that. We're not going to need to do that. But after you finish this class, if you're somewhere, someplace, that's just so you know, there is another thing to do. If the population is not symmetric and you have a large sample, um, we actually don't even care if it's symmetric or not. If you have a large sample, this is why I don't like this flow chart that well. You're just back here in this yes situation where if you know sigma, you're going to do z-test. If you don't know sigma, you're going to do a t-test. Okay, so if it is not symmetric and it's not a large sample, then it requires yet another procedure that we are not covering. Okay, so that's it for chapter 9, and there is a quiz on Monday.